section 13.6 is a fairly short section. We're just going to take a moment and take a step back and just really highlight one of the most important applications of vector functions. And that's for describing motion in space, where our r of t would be a position function. And we've seen then that that means that r prime of t, which if I wanted to, I could call v of t, is going to equal the velocity function. And the magnitude of r prime of t is then the speed of that. And of course, we've seen that the magnitude of the derivative is the rate of change of arc length with respect to the parameter t. So in this case, that would be the rate of change of arc length with respect to time. Of course, the length of the curve, if it's a position function, that curve is the path that we're traveling, so that the length of the path that we travel is the distance that we travel. Okay, and rate of change of that with respect to time, of course, we call that speed. Okay, excellent. Then we also have that the second derivative of position, which would be the first derivative of velocity, I can call that a of t for acceleration. And of course, anytime I've got this relationship in terms of the derivatives, that's going to give us antiderivative relationships as well. Okay, then we've got that if I integrate r prime of t dt from a to b, just looking at a couple of definite integrals here, this would give me the displacement. So just like with real valued position functions, if you integrate velocity, you get displacement. With a vector function, displacement is a vector. It would just point from my starting point to my ending point for whatever path I had traveled. Okay. If, on the other hand, we integrate from a to b the speed, which is the magnitude of the position, I know generically that's my formula for arc length. Again, with a position function, the arc length is the length of the path. That's equal to the distance that you traveled. Okay, so we've seen these relationships before. Just wanted to really highlight those and emphasize them because that's important. And in the textbook, they talk a lot about projectile motion. So that's if you throw something up into the air, trying to determine its path. Now, if you throw something up into the air, if we neglect air resistance and things like that, the only real force acting on things is the force of gravity. And so you can derive the formulas for that, the path of an object that's thrown into the air. Now, those of you who are taking physics may very well have accidentally or on purpose memorized those results. So I'm actually more concerned with the process. So I'm going to suppose that we're on a totally different planet where acceleration is a function of time, but acceleration acts to the left and up. So the acceleration is constant, just like it is here on Earth, but it's pointing left and up. Okay. That way, those of you who've accidentally memorized the results for starting with the acceleration due to gravity here on Earth and then working your way back to a position function don't have that advantage of knowing what we're supposed to get. Okay. So what I want to do is suppose that the acceleration due to a weird leftward, upward gravity is the only force that's acting on an object, that acceleration is constant, and I want to try to work backwards to try to find the position function. Now, in order to do that, I'm going to need some initial conditions. So letting r be position, let's suppose I know that r of 0 is 5, 4, and r of 1 is 2, negative 3, and then I want to find r of t. So this is an initial value problem. We're starting with acceleration, which is a second derivative. So I can tell I'm going to integrate once to get velocity. Then I'll have to integrate a second time to get position, and that's why I need two initial conditions in order to get a unique answer. Sometimes those two initial conditions would be one position and one velocity. Here I'm giving you two positions. Okay, so let's see if we can't find our position function. So I would say the velocity is an antiderivative of the acceleration, because this is just the derivative of velocity. So we're going to be integrating -1, 2 with respect to t. So that's going to give me -t, 2t plus c1. I know I'm going to be integrating a second time, so I'm just going to automatically call my constant of integration here, which you'll notice is a vector. I'm going to call it c1 rather than just c. Okay, now if I had a velocity at a particular time, I could plug in and solve for what c1 is. Not having that, I'm going to have to integrate again to get my position function. So now I can say r of t is going to be an antiderivative of v of t. So that's going to be an antiderivative of -t, 2t plus c1. Very important that I don't just integrate this. This is just a constant, but when I integrate a constant, I'm going to get something, and that's going to be part of my formula for position. So let's see what we get. We're going to have -t squared over 2, comma t squared, plus c1 times t, because when you integrate a constant, you get that constant times t. Actually, let's write the t first, because that's essentially a scalar by which we're scaling this vector. And then plus c2, plus a second constant. Okay. So there are two constants of integration that I'm solving for. And again, that's why I needed two initial conditions. So now we can use our initial conditions to try to solve for those constants. If I look at r of 0, that was supposed to be 5, 4. But I also know that r of 0 is what I get if I plug in 0 for t. Now if I plug in 0 for t here, this vector just goes to 0. Then I'm going to get 0 copies of c1 plus c2. So that's very nice. That tells me that c2 is just 5, 4. So I've got that one. Let's see. Let me clear some space here. So at this point, I can say r of t is -t squared over 2, t squared, plus t copies of c1, still don't know what that is, but plus c2 is just 5, 4. And now I can use my other initial condition, r of 1, that's supposed to be 2, -3. That's going to be what I get if I plug in 1. Now if I plug in 1, I'm going to get -1/2, 1, plus 1 copy of c1, plus 5, 4. Let's just combine these. That's going to give me 4.5, or 9/2, comma 5, plus c1. And that's equal to 2, -3. So I should be able to solve for c1. So I'm going to just subtract this over. So this would have been 4/2 minus 9/2 is -5/2. -3 minus the 5 is going to be -8 is equal to c1. Put the pieces together. r of t is -t squared over 2, t squared, plus t copies of -5/2, -8, plus c2, which was our 5/4. Okay. All right. So some of the problems in the homework are going to ask you about projectile motion, where the book has already derived the formula for r of t. You can feel free to just look that up and use it. But do make sure you understand how to start with acceleration, integrate to get velocity, and integrate again to get position remembering that each time you do that, you get a constant of integration. Okay. So just an application of initial value problems. Just wanted to review that.